Okay, welcome back to our third segment for today. And we've been going over a lot of important stuff fairly quickly. So I'm going to try to keep it short on this third segment, just to sort of give you time to catch up on what we've been doing. But I will at least want to introduce the subject of dilution of solutions. Dilution is an important concept. We're probably familiar with it in everyday life from any number of different instances. Dilution essentially means adding more solvent to a mixture. So the volume goes up, but the concentration goes down. In cases of molarity, you can look at the equation for molarity. Molarity, remember, is a number of moles of solute divided by the volume of the solution in liters. And if you add more solvent, not solute, just solvent, that's all you're adding, it has no effect on the numerator of this equation, but it does increase the denominator because the denominator is the entire solution. And when you add more solvent, that's part of the solution. So the volume goes up. And so you're dividing the same number by a bigger number, and the result ends up being smaller. So that's why dilution increases the volume, but it decreases the concentration. You can even see it like thinking about maybe diluting a bottle of Windex. You know, it starts out that characteristic Windex blue color, but if you add a bunch of water to it, it's going to be a paler blue, right? And that's because you're decreasing the concentration of whatever it is that makes it blue. Okay, so as we said, dilution or adding more solvent has no effect on the number of moles of solute dissolved in the solution. So the number of moles of solute in the solution remains the same during a dilution. And the number of moles of solute in a solution can be thought of as molarity times the volume of the solution in liters. Number of moles is often denoted as N. And if you want to think about the situation before a dilution versus after a dilution, then you can think of, say, the number of moles of solute in a solution before you dilute it as being M1V1. That is, you know, the original first molarity times the original or first volume. And you can think of the number of moles of solute dissolved in the solution after you dilute it as being M2, that is the later or the second molarity, times V2, that is the new or the later or the second volume of the solution after you dilute it. So moles of solute before dilution would be M1V1, and moles of solute after dilution would be M2V2. But as we saw up here, number of moles of solute doesn't change during dilution. So these two things have to be equal. And so we come up with the equation that we characteristically use for dilutions, which is M1V1 equals M2V2. So during any given dilution, the molarity will go down as the volume goes up. And they always go up or down by the same factor. So if you double the volume, you cut the molarity in half. Okay, and so one times the other will always come out to the same result for any solution. And so molarity times volume before dilution will be equal to the new molarity times the new volume after dilution. Okay, so M1 is the molarity before dilution, V1 is the volume before dilution, M2 is the molarity after dilution, V2 is the volume after dilution. The reason I'm using V here instead of L like I did when I was talking about molarity is the fact that the volume doesn't necessarily have to be in liters. You could use any units for volume you want as long as you use the same units for V1 and V2. You could use units of cubic feet for volume. That would be kind of a crazy unit to use. It's totally non-metric and it's hard to calculate, but you could do that. And the equation would still work as long as you use cubic feet for both V1 and V2. Also, the concentration doesn't necessarily have to be in units of molarity. This equation works for most ways of expressing concentration also. So it's sometimes written as C1V1 equals C2V2. Molarity so far is the only unit for concentration that we've seen, but later on when we see more, you could use those units of concentration too, as long as you use the same units of concentration for M1 and V1, or C1 and C2, or sorry, M1 and M2, or C1 and C2. You could use, mass percent as one of the other concentration units I used. You could use mass percent for concentration 1, as long as you use mass percent for concentration 2 also. Okay, this is important because dilution is something that we do very, very often in lab. Most of the, I know that we went virtual with the labs before we really saw any significant number of solutions in the lab. But the way that as we go forward, you can just sort of think about it as you're reading over the labs in the future. The way that most of the solutions that we talk about in the lab, or that we will be using if we ever actually get back to the lab this semester, are made up by me by diluting more concentrated solutions that we purchase from chemical suppliers. So, like for instance, hydrochloric acid comes from the supplier in a concentration of 12 molar, which is really concentrated, very powerful stuff. And it's actually pretty dangerous to have around. That's why we keep it locked up in the stockroom and don't actually let the students use it. But if we, a lot of experiments call for smaller concentrations of hydrochloric acid. And the way that I make those is I take the 12 molar hydrochloric acid, handling it very carefully, and dilute part of it to whatever molarity we need for the experiments. So if you had, so for example, if you want to make 500 milliliters of a 1.25 molar hydrochloric acid solution from a stock bottle, that's what we call the bottles that we keep in the stock room, where the concentration is 12 molar, then what volume of the stock solution, that is the 12 molar stuff, should be used? And this is the kind of calculation that I do for lab all the time, because I know what concentration the book calls for the hydrochloric acid solution, and I will estimate how much we need based on the size of the class and how much each person has to use during the experiment. And then I usually add a little more just to be on the safe side. And so I'll know the concentration of the solution I'm starting with, and I'll know the concentration of the solution I want to make, and I'll know how much of it I want to make. The question is, how much of the original more concentrated solution do I need to measure out? And so using the equation M1V1 equals M2V2, M1 would be the original concentration. We usually assign M1V1, M2, and M2 and V2 chronologically. So if you read a word problem, you just sort of think about the order in which you would be doing things. In this question, I would be starting with the 12 molar stock solution from the stockroom. And so that is what I call M1. And then I'm going to turn that into the 1.25 molar solution. So that comes later in time. So I'm calling that M2. And the corresponding volume of that 1.25 molar solution would be 500 milliliters. And the corresponding volume of the 12 molar solution that I need to use is unknown. So that is a question mark. So what we need to solve this equation for is V1. Okay, so that's why I have V1 circled here. That's what we're solving for. If you just rearrange this equation algebraically, M1 V1 equals M2 V2. If you want to solve for V1, that just means you need to get V1 by itself on one side or the other. It's already on the left side, so it'd probably be easiest just to leave it there. That means, though, that you have to cancel out M1. You can do that by dividing the left-hand side by M1, then it cancels out. But to keep the equation equal, you have to do the same thing to the other side. So now M1 is on the denominator on the right-hand side, and it does not cancel out. So that has to stay there. These cancel out and can go. So we end up with the equation V1 equals M2 V2 over M1. And then just plug the numbers in. M2 is 1.25 molar. M2 is 1.25 molar. V2 is 500 milliliters, and M1 is 12 molar. Note that when we work all this out, the molarities cancel out and you end up with units of milliliters. So it actually is okay to use volumes in units other than liters, as long as basically, well, in this case, if you put in milliliters, that means you're going to get milliliters as the unit for the answer. And that works out to 52.1 milliliters. So what I would have to do is measure out 52.1 milliliters of the 12 molar hydrochloric acid. And then I would have to add distilled water to that until the total volume is 500 milliliters. It's important to remember that V2 is the total final volume of the entire solution. V2 is not the amount of water that you need to add in order to make the dilution. It's the total final volume. So I take the 52.1 milliliters of acid and add water to it until the total volume is 500 milliliters. If you want to know how much volume of water, DH2O just means distilled water. And that's the kind we use in the lab because it's more pure than tap water. The volume of water added is V2 minus V1, the difference between the original and final volumes, because that's how you're going to get from the original volume to the final volume, is by adding more solvent, which in general chemistry is almost always water. So the volume of water added is just the difference, V2 minus V1. 500 minus 52.1 is 447.9. That's how much water I have to add. Okay. Molarity, or sorry, M1 V1 equals M2 V2, of course, could be solved for any one of these four variables, depending on what you know and what you need. So just as a quick other example, we have, if you have 37.5 milliliters of a 0.685 molar solution of sodium chloride, and you add 125 milliliters of water to it, what is the concentration of the final diluted solution? Okay, so here you're starting out with the 0.685 molar solution, and you're adding water to it. So M1 is going to be 0.685, and V1 is going to be the 37.5. And the new solution will be M2 and V2. M2 is the unknown. V2, now remember, V2, the catch here is V2 is the total final volume of solution. I said here that I add 125 milliliters of water to the solution. Okay, so the total final volume is going to be the 125 I added plus the 37.5 that was already there. So V2 is 37.5 plus 125, which is 162.5. Now we can go to the equation. M1 V1 equals M2 V2. If you solve that for M2, that's just M1 V1 over V2, using the same kind of algebra we just used in the question above. And M1 is 0.685 molar. V1 is 37.5 milliliters. V2 is 162.5 milliliters. Notice that the units for the volumes cancel. That's why you can use any units you want for volume, as long as you use the same units for V1 and V2. That way they'll cancel. and molarity is the unit that's left over. When you work all of this out, we end up with 0.158 molar. You can also kind of check to make sure that the answer at least goes in the right direction, because this is a dilution here. The new molarity should be smaller than the old molarity, and it is, because that's what dilution does. It decreases the concentration. Also, the new volume should be bigger than the original volume, because that's what dilution does. It increases the volume, and it is. So that's good. Looks like it worked out. A third example, and just a quick one. If you have 85.0, I added the 0.0 in to make it 3 significant figures, of 1.80 molar HNO3, what volume of 0.720 molar HNO3 can be prepared from it? So in this case, 0.720 molar is what you're going to prepare in the future. What you've got right now is the 85 milliliters of 1.8 molar HNO3. So M1 is 1.80 and V1 is 85.0. That 0.0 is there in spirit at least. And M2 is 0.720 and V2 is the unknown. Okay, so M1 V1 equals M2 V2. Solved for V2 would be M1 V1 over M2. And that's M1 is 1.8 molar, 1.80 molar. And V1 is 85.0 milliliters over M2, which is 0.720 molar. Notice the molarities cancel and you end up with milliliters for the volume. And that would be 212.5 milliliters. Although for 3 significant figures, you'd have to round that off to 213. And that is the total final volume of the solution. Notice I also asked what volume of water would I need to add to the original solution to accomplish this dilution. So again, volume added is just V2 minus V1, which is 213 minus 85.0. That's 128 milliliters of water that I would need to add. Okay. So just keep in mind the difference between the total final volume, which is V2, versus the volume of water that you have to add, which is the difference between V2 and V1. I'm going to leave it there, even though we're a little short of our usual time for the third segment, just because, like I said, we've been covering a lot of stuff fairly quickly, and this is a fairly short chapter. So we will definitely be finishing up this chapter in Tuesday's lecture. Just to give you a heads up, that means that the homework problems for this would be due next Thursday, a week from today. So be sure that you're working on those and trying to keep up. Okay. I didn't realize when I first started this chapter how short it was. So that's why I'm kind of slowing down a little bit. Don't want to go too fast. Okay, so we'll start with 3.4 next time, and I'll see you then.